Guys, today we're doing a AS Maths Mechanics 1 paper. So we'll get started. Okay, so this first question, not too difficult. It's all about balancing forces. So you've got this particle in equilibrium, and that means that the forces are all balanced along all perpendicular directions. So if you think of the x axis, so we're defining our axes like so, x and y, then the forces in the x direction are firstly this force going to the right, F, completely along the x-axis, and a force going on the left, which is if this is the tension, then this must be T sine of alpha, because this is a right angle triangle. And so you know that if it's in equilibrium, then F must be equal to T sine alpha. Well, it's all very well, but we don't have T either. So we need to first find T. Well, for that, we can look in the y direction. And we know that there is a component of T in the y direction, this guy up here, which is T cosine alpha. And we know that this thing is also being pulled by gravity downwards by a force mg. So we have in the y direction, so this was the x direction. In the y direction, we have that mg must be equal to T cosine alpha. So if I divide these two, on the left hand, I get F over mg being equal to tan of alpha, because the tan is equal to sine over cosine. Okay, so this means I can solve for F. So F must be equal to mg tan of alpha. And this gives us, this is equal to 1.6 newtons, because we have mg, well, we have m, we know what g is always 10, and we're given the tan of alpha. Now we just have to plug it in over here, and we can get that T is equal to F over sine of alpha. And the best thing here is just to use our calculator, and we know that the sine of alpha is equal to the sine of the inverse tangent, just using our calculator, of 8 over 15, because we're given that the tan of alpha is 8 over 15. And this gives us that the tension is equal to 3.4 newtons. So it's just having to balance both in the x direction and the y direction. And that gives you all the answers. Okay, the second one is kind of similar, except now we're bringing friction into it. So first we're asked to find the total work done by the forces shown in the diagram. So you have this thing moving in the x direction at some constant speed. So where is the force of friction acting? Well, the force of friction always acts opposite to the direction of motion. So the force of friction must be acting completely out back here. So these two forces are acting in such a way that they pull the thing at a constant speed. If there was no friction, there would be a net force pulling the thing to the right, and it would accelerate. But because there's no acceleration, we know that the forces must be balanced. So, you know, equilibrium, this thing is in equilibrium, does not mean at rest. It means that the forces are balanced, which is another way of saying that no acceleration. So there might be a velocity, a non-zero velocity, but just there's no acceleration. So this thing is in equilibrium because it's moving at a constant speed. So again, the forces have to be balanced. So how do we work out what's going on? Well, we have some force along the x direction, some net force, which is 0 because the thing is in equilibrium. And that must be equal to the x component of this guy, which is 30 cosine alpha, plus the x component of that guy, which is 40 cosine beta minus the force of friction, which is this guy. So that is all our forces that are acting in the x direction. And we've just resolved these forces along it. And we know this thing the whole thing must equal 0 because the thing isn't accelerating in that direction. So we know 30, we know what 30 is, we know what the cosine of alpha is, we know 40, we know what the cosine of beta is. And this gives you that the force of friction is equal to 50 newtons. Well, that's great. But what we want to know is the total work done. And work done is basically the work dissipated through friction. Because if you accelerated the thing, you would be putting work into increasing its kinetic energy. If you raise the thing a height, you would be putting work into raising it that height and increasing its potential energy. But we're not doing any of that. All of the work we're doing is going into fighting the force of friction. So the work done is the force of friction times the distance, which is 1,000 joules. Okay, so given that the coefficient of friction is 5/8, so this is mu, what is often called mu, we know that the force of friction is equal to mu times r, where r is the reaction force on the ground. The only thing pushing the thing into the ground is the weight of it. So reaction force is just mg. So this is equal to mu mg, which is equal to 50. So if that's the case, mg, which is the weight, is equal to 50 over mu, which is equal to 80 newtons. No problem. Okay, question 3. So we have a cyclist going up this hill, and you have to be pretty careful with directions in this problem. So his driving force is up the hill. I'm going to call that F. In fact, it is called F. The resisting force is down the hill, and it's magnitude 32. They're just saying a resistance to motion, and that doesn't include the weight of the cyclist. And in fact, the cyclist is moving down, he's moving uphill. So it probably is just the force of friction. I mean, maybe some air resistance, force of friction on the tires from the rough ground, and so on and so on. But we're just told that the total thing is 32. There is a reaction force, and that's going to be equal to. So this is this angle alpha, right? And we know with these ramp problems that if that wedge angle down there is alpha, then this angle here is also alpha. So then this force is mg cosine alpha, and then the component of the weight acting down the hill is mg sine alpha. So what do we know? We know, so for question 1, we know that the net force acting along the ramp, so I'm going to write my coordinate system like this, x and y. So x is kind of defined as positive going up the ramp, not like this, but up the ramp. So the net force in the x direction is F, which is acting up, minus 32, which is acting down, minus mg sine alpha. Now this must be equal to m times the net acceleration. You see? So we know that the net acceleration is actually negative. So the net acceleration is actually going to be acting like so. That's minus m times 0.2. And that's just why I meant you have to be careful about directions. He's not actually accelerating up the hill. He's moving up the hill, but his speed is getting smaller and smaller. So we know that the total weight of the cyclist and his bicycle is 780 newtons. That's mg. And you can solve this. So we know that m must be equal to 78 kilograms. So therefore, we know 32, we know mg, we know sine alpha, because we're given it. We know m, and we know the acceleration. So this gives us that F is equal to 102.8 newtons. Okay, so now we're asked to find how far uphill the cyclist travels before coming to rest. And for this, we can use the equation final velocity squared is equal to initial velocity squared plus 2 times acceleration times distance traveled. And if you just plug in all of these, you know that the final velocity is equal to 0 because the cyclist is at rest. And you get that the distance is equal to 122.5 meters. And you just plug all that in. And you see that, again, that this will be, A will be negative. So you'll get that, we'll just write it out, S is equal to minus V naught squared over 2A, which is minus 7 squared over minus 0.4. And that's all you need to do for that question. Okay, question 4. So we have particles P and Q moving in a straight line. So this question is actually a little badly phrased, I think. It's not quite clear what the situation is and which direction the particles are moving in. But what you should know is that they are both moving in the same direction. So you've got particle P moving like so, and particle Q moving like so. And the Q is decelerating more than P. So eventually they're going to meet. So at some point, we'll deal with question 1 first. So question 1, you want the deceleration of each of the particles. So we know that the force on a particle is equal to the mass times the acceleration of that particle. And in this case, the only force on the particle is the friction force, mu r. And the only reaction force is mg. So we got mu mg. So you see that if you have this equation, ma is equal to m mu g, the m's cancel. So acceleration is just equal to mu times g. So the acceleration of P is equal to 0.2 times g, which is 2. And similarly, the acceleration on Q is equal to 2.5. Okay, so now it becomes important to think about this physical situation. So if I have some point A, which P is passing, at the same time that Q is passing B, and then eventually, so let's just move that a little. Oops. Let's move that over there. And then at some point later, they will collide at some point C. So just to make this absolutely, physical, at some point C, they will collide. Now they will collide because they are decelerating at different rates. Q is actually getting slower. It's going to be slowing down quite a lot compared to P. So let's think about this distance. We know that the distance from A to B is 5 meters. And I'm going to call this distance from B to C L. So let's think about the motion of A. Well, we can use the constant acceleration equations. And we say that A has to move 5 plus L meters. And that's going to be equal to initial velocity of A times time plus 1/2. In fact, excuse me, I should have actually made it clear that these are going to actually be negative. I think it's just about remembering which directionality you're talking about, but I'm going to say that they're negative because they're decelerating. If I define that as my positive direction. So it's going to be 1/2 plus 1/2 A P. So this is the motion of P rather. P, not A is just the point, VPT plus 1/2 APT squared. And what about the motion of Q? Well, it has to move L meters, and that's equal to initial velocity of Q times T plus 1/2 acceleration of Q T squared. So that's, so therefore, if I just take the 5 on this side, minus 5, I get that 8T, and I plug in all the values of VP and AP, and remembering that AP and AQ are negative, 8T minus T squared minus 5 is equal to 3T minus 1.25 T squared. And then I rearrange this to get T quadratic equation, and I get that T is equal to 0.95445 and so on seconds. Now I can use this to find the speeds of P and Q, just using the formula V final is equal to V initial plus the acceleration times the time. So the velocity of P at the end is equal to the initial velocity minus 2 times this time that we found, and so on. You can plug that in. Okay. Question 5. So we have this lorry climbing up a straight hill. So let's draw a wee picture. And it's 1440 meters along here, but the hill itself is 16 meters high. So this is going to be a very small angle, right? This is a conservation of energy question, really. So you can see that when they start talking about work done and stuff, they're talking about conservation of energy. So let's consider the situation between the bottom of the hill and the top of the hill. Well, what is the initial energy? Well, it's at the bottom of the hill, so it's got no potential energy, but it's got an initial speed. So its initial energy is 1/2 mv squared. And its final energy, well, it's moving at the same speed, so the kinetic energy is still 1/2 mv squared, but now it's got some extra potential energy. So there was this gain in the there was a driving force acting on the truck, and the driving force didn't have any effect on the speed of it. All of the driving force, so the work done by the driving force, all of it went into raising the truck 16 meters up and fighting the force of friction, because there was friction, but the thing didn't slow down. So it must have been, the driving force must have been doing work in order to fight the force of friction. And that's the resistance to motion, by the way. Well, this is very easy. So the best thing here, when you've got these, questions about cars and lorries and things, often the numbers are very big. So I'm going to express everything in scientific notation. I'm going to say that this 15,000 is equal to 1.5 times 10 to the 4 kilograms. This is 1.44 times 10 to the 3 meters. And this is 1.8 times 10 to the 3 newtons. So I have that mg, so g is just 10, so this is 1.5 times 10 to the 5. That's the weight, mg, times the height, 16, plus 1.8 times 1.44 times 10 to the 6. And you will find that this is 4.992 times 10 to the 6 joules. It just makes it easier to work with things that are very, different orders of magnitude. Although, if you're careful, you don't have to. But really, it is better to use scientific notation for these things. And imagine writing out 6, a whole nother 4992000. It's just hard to keep track of. So, next question. Now they're saying that after reaching the top of the hill, the truck travels along some straight section of road with a different speed, with a higher speed, and that it's still fighting some resistance to motion. So they're saying that they're now giving us the work done, and they want us to find the work done by fighting friction. So the work done by the driving force, again, is equal to the change in internal energy plus the work done for friction, right? So the change in the internal energy is the change in the kinetic energy. So it's 1/2 V final squared minus V initial squared, So that's the change in the internal energy because it's sped up from 15 to 24. And the work done by friction is the sort of work done over the resistance force times friction, like work is force times distance, right? So this is going to be the force of friction times the distance. Well, we have the work done by the driving force, and we're going to say it's 5 times 10 to the, now kilo means, there's already 1,000 joules. So in SI units, everything is, you need to talk about joules, not kilojoules. The only exception is kilograms, because for historical reasons, we don't use grams as the SI unit, we use kilograms. But we don't use kilojoules, we use joules. So to get this in SI units, that's going to be 1, 2, 3, and then additional 4, 5, 6. So 5 times 10 should probably be a bit more exact. 5.03 times 10 to the 6. That's the driving force work done by the driving force, is 1/2 times the mass, which, if you recall from up here, was 1.5 times 10 to the 4. Final velocity squared is 24 squared minus 15 squared plus the force of friction, 1,600, times the distance. And you can see that you can solve for D here, which is what we're looking for. So everything else is numbers. Okay. Question 6. So this is one of the situations where you have two objects. This happens a lot, basically things on pulleys, where they sort of move in tandem because they've got this light, inextensible string. Well, that means that the tension is the same everywhere in the string, and string accelerates all together. So it's inextensible, meaning it can't be squished or stretched. So every piece of the string must move together, which means anything attached to the string has to move all together. So T, the tension felt by B is equal to the tension felt by A, and the acceleration of A is equal to the acceleration of B. And this is the fact. These are the two facts that allow us to solve this problem. So let's look at the situation for A. Well, it's got tension acting upwards, and it's got MAG acting downwards, and it's moving. So the net force, I'm going to define my positive sort of direction as whatever it takes to be going over this way. So for A, it's going up, and for B, it's going down. So the force on A is T minus mag, and this is equal to ma times the acceleration. And for B, we've got a similar situation. But now the net force acting on B, I'm talking about downwards being the positive direction. So this is mbg minus T. And this is equal to mba. So if I add both of these together, the T's cancel out. I get ma plus mb times the acceleration is equal to ma g plus mbg. Wait, that's not quite right. Ma, right, sorry. This is equal to mbg minus mag. Well, ma plus mb is 0.3 plus 0.7, so this is just equal to 1. And this is going to be equal to 7 minus 3, which is minus 4. And, oh goodness, which is plus 4. So A is equal, A is equal to 4. 4 meters per second. And so the whole thing is being accelerated like that. Now we can just plug that into this equation to find T. So if T is equal to 0.3 times 4 plus 3, which is 4.2 newtons. Okay, so this is just a repeat of the same question. Now they're asking us to find the time. So at some point, they're both moving at 1.6 meters per second, and then the string breaks. So now both particles are just going to fall freely. So we have some situation a little later on, and maybe A is up here, and B is down there, and it's gone up some distance s. And now the string gets broken. So at this point, it's moving at some velocity, 1.6 in fact. So we can use that equation again, that V final squared is equal to V initial squared plus 2AS, where it starts with V initial is 0, because this, I'm talking about the motion of A between here and up here. So it's just under constant acceleration, right, which we found before, just be 4 meters per second. So we can use this equation. So if we solve, we know the V final, this is 1.6, and we know the acceleration, which is 4. So if we solve this for S, we get that S is equal to 0.64 meters. Well, that means that the total height, H, above the ground, height of A above the ground, is this height 0.64 plus 0.52 from before. So this is 1.16 meters. Now we have a situation where it's under free fall. The tension in the string is no longer producing any acceleration for the, any force and any acceleration for A. The only acceleration is G. So the new acceleration is equal to G, which is 10. Right? So now we have something, and we have the situation. We know now for our new situation, V initial is now equal to 1.6 meters per second. And the height, we can therefore impose conservation of energy. Actually, we don't know. We shouldn't do that, because that would, no, that's no good. What we need is the time taken, so we're going to have to use kinematics. You can't use conservation of energy for time taken. We have that the initial velocity is 1.6 meters per second. So we have the distance traveled, let's call it D, distance traveled, which is 1.16 meters, because it goes from up there to the ground. And that's equal to v initial minus v initial times, so directionality is important here. So now, so the point is that it's traveling downwards, but its initial velocity is actually upwards. So if I'm defining downwards as my positive direction now, I've switched, that means that the initial velocity is actually negative. If you want to just keep defining upwards as your positive direction, you can do that, but then the distance becomes negative because you're moving downwards. You see? So you just have to be careful and make everything consistent. Otherwise, you will make, it does lead you to make mistakes. So this is minus 1.16 t, and then the acceleration is in, so plus 1/2 g t squared. Wait, this is not 1.16, it's 1.6 because that's the velocity. And here the acceleration is positive because I'm treating downwards as the positive direction, but you can do it the other way. And if you just solve this for t, you get two solutions, of course, because it's quadratic, but one of them will be negative. Sorry, one of them will be, one of them will come first. One of them will be applicable. So usually in these situations when you've got times and you want like the time something reaches the floor, you're not interested in any negative times because you can't have negative time because that would be before your experiment started. And you don't want, you want the first positive time to occur because it doesn't matter that your equations predict that it's going to crash to the ground and then crash to the ground later on. That's just a relic of the mathematics. The first time it crashes to the ground, that's when it crashes to the ground. It doesn't then, you know, sometimes the mathematics itself doesn't know that once something has crashed and has reached the ground, it stops. The mathematics might just think that it carries on and then comes back to the ground and so on. Anyway, the point is you'll find two answers for t, but only one of them will be valid, and that's 0.6 seconds. Okay. Question 7. So this is all about differential equations. So we have our particle P, and it's going to start at this point O, and it's going to head outwards. And we're given the acceleration. So what is the acceleration in terms of derivatives? Well, the acceleration is just equal to dv dt, right? And in turn, v is equal to dx dt. We'll get to that in a second. So we've got the acceleration is equal to dv dt, and that's equal to 0.6 t. So we're going to use, we're going to rearrange this and use separation of variables. So we bring all the v's on the left-hand side and all the t's on the right. Well, there aren't any v's except for dv, so we just have dv is equal to 0.6 t dt. Now I'm going to integrate this. And as I've said before, there are two, if you're given some kind of boundary condition, you can just go plus c if you want. But the boundary condition in this case is that at t equals 0, the velocity is 0 because it's telling us that it's from rest. But you can also just put those into the limits. So I'm interested in my progress from a time equals 0 to some later time. Let's just keep it general. So at time equals 0, my velocity is 0, and at some later time, my velocity is some velocity, function of time. So I'm going to integrate this, and I'm going to get velocity at some time is equal to 0.6, and then I integrate 1/2 t squared from 0 to t, which is just equal to 0.3 t squared. No problem. That means that at t is equal to 10, v is equal to 30. And now I want to find the displacement. Well, now I use this v is equal to dx dt. This is why I kept v general. So I have dx dt is equal to 0.3 t squared. I use separation of variables again. I get that integral over dx is equal to 0.3 integral of t squared dt. And I look at my boundary conditions again, at t equals 0, x is equal to 0. There's no displacement yet. And at some later time, t is equal to t, and x is some x value at that time. So this gives me that x of t is equal to 0.3 over 3 t cubed. And therefore x at 10 seconds is equal to 100 meters. Great. So you see the advantage of keeping it general. I want a general expression for x at time t, and then I plug in. And that allowed me to just use this v of t. If I'd plugged in 10 seconds here, it wouldn't have been very helpful. So part 2. So now we have a different kind of motion. At 10 seconds, the motion changes. So the differential equation has changed. In fact, it's decelerating. So we're going to have to repeat this procedure. So we have, I'm going to call any t that's greater than 10 seconds, I'm going to call this t prime, just to make it clear. You'll see why that's useful. So dv dt prime is minus 0.4 t prime, that's what we're given. And this t prime, I mean, it doesn't start from 0 at 10 seconds. It's just my bookkeeping. It's the same time as before. So here I'm again going to separate variables, and I'm going to go dv from 10 seconds to, from the velocity at 10 seconds, which was 30, to some velocity at a later time, is the integral over time from 10 seconds to that later time. Well, this means that v of t prime minus 30, so that is actually minus 0.4 integral dt of dt prime of t prime from 10 seconds to some later time, which is minus 0.4, and then divided by 2, so it's minus 0.2 t prime squared between 10 seconds and t prime, which gives you that at v is equal to 0. Okay, well, let's solve this. Let's just write this properly. So we get that v at t prime minus 30 is equal to minus 0.2 t prime squared minus 10 squared. That's a 10 there. And this gives you the sort of general expression. Put it over here. General expression for v. V of t prime is equal to minus 0.2 t prime squared plus 50. That's great. And the reason I've kept it general is because this we now know is dx dt prime. So how x is changing with t after t equals 10 seconds, because the motion has changed. Well, again, I therefore separate variables. So we're returning to this, this is how x is changing anytime after 10 seconds. So we're going to integrate from whatever x was at 10 seconds, which was 100, to our final x, OA. And that's going to be equal to the integral over time from 10 seconds to this final time. In fact, let's just work out what that final time is, because we know that at the final time, the velocity is 0. So v is 0, and we just plug in 0 here, and we rearrange all of this, and we realize that after 10 seconds, the velocity is 0 when t is equal to 5 square root of 10. So in fact, our upper limit here, when x is equal to OA, the time is equal to 5 square root 10. And we're integrating minus 0.2 t prime squared plus 50. So this means that OA minus 100, which is what on the left-hand side, is equal to minus 0.2 over 3 t prime cubed plus 50t, evaluated between 10 and 5 square root 10. And this will give you that OA is equal to 194 meters. So that was quite a complicated job that we had to do. It's all about, this is why I tend to always use the technique of matching limits. Because if you do the indefinite integral plus c and then solve for c, things aren't just, they don't carry forward to more complicated problems very well. So the big idea here was to always keep things as general as possible until you need to plug something in. So don't just integrate between definite limits. You can integrate, if you just have one definite limit, a boundary condition, you can use that as one of your limits, and then the other two are going to be just some general later time. So when I was in the first regime, where the acceleration was this, the first amount, these limits were valid within that time. Then when the motion changed, I had to integrate from the beginning of this new regime to some later time after that. And I kept it general, and then I could use the fact that v is the xct, acceleration is dv dt. So yeah, this one was a bit tricky. Please feel free to ask me questions if you on the forums if you have any questions about this stuff or struggling with any similar problems. And I'll see you next time.